Hello everybody, welcome to another stream. How we doing? So, last stream, I don't really have a proper working build, but I've got this. I guess it's mostly working except for the fact that it's got the wrong texture and I can't compile the existing code at the moment. It's in a work in progress state. So last stream we basically got the octahedral mapping working. So if we open up the texture viewer, it looks something like this. So this is being the sphere normal is being mapped to this basically, right? And so here you go, it's got 4 sides there and 4 sides there, yeah. And we also got in some test code for using the right MIP level. There's the 4 sides at the back, 4 sides at the front. We also were writing some code because we sample these textures in a compute shader and we need to manually calculate our MIP level, and we managed to get a kind of a version working, but that wouldn't work across all of the different ray tracers I have, and it also wouldn't work across the boundary. It doesn't also work across the boundary on the octahedral layout. So you'll notice there's some sort of like flickering here where the edges, the boundaries of this octahedral map. So when we move, you'll see that even here as well, there's this sort of pixel like flickering going on. And that's because the way the octahedral map works is that when you sort of take the normal, what's the way of saying it? Yeah, here it is. If you just to have a normal from this point here and slide it across until you go into the red, the route that will take is in the texture space is actually different. So you would start here-ish, it would go down instead of going to the right, and then kind of reappear all over here and go back up, right? So that's just because of the way of the octahedral map works. So that means that the way I calculated the MIP level initially was I did it in UV space, like in texture space. And of course, if you have one pixel which is on the left and a neighboring pixel which is on the right hand side, so one is on the black side, the other one's on the red side, and you sort of swap their UVs and take the difference and use that as the DDX and DDY into the sample gradient function. What you get is 1 pixel over here, 1 pixel over there, and you've taken the difference, and therefore it's thinking that the sampling area is very wide, so you'd end up picking a MIP which is all the way like down here or something. Probably one of these MIPs, to be honest, or maybe even like something like that or something like that, and you're just getting that color being shown up here because it's just sampling from that. Now, so I was looking at ways that we can calculate the MIP level in a different way. So we're going to calculate the derivative between 2 neighboring pixels. So I was looking at just Googling a whole bunch for like ray tracing, and this one popped up here by Inigo Quelles, the guy who makes Shader Toy and has all the SDF articles and things. And it's quite clever and simple. So you just basically ray trace against a plane, the tangent plane. So I've asked to make that into a drawing. I'll do another one. So you have your sort of ellipsoid or sphere in this, right? And so when you have your sort of camera up here, and you shoot your ray and you hit this surface point here, yeah? What you do is you have you sort of treat that as that sort of direction as a normal for the plane, and then you make another ray direction which goes through the neighboring pixel to the right and one which goes to the neighboring pixel up. So you go like up 1 pixel and to the right by 1 pixel, and then you do a ray verse plane, and you figure out, you get the other two spots, one going up and one going to the right, for instance, and that gets you your DDX in world space. Well, no, in local space this might be, yeah, and your DDX and your DDY in local space. So that'll be the difference between your current pixel and the pixel next to us. What is the difference in the coordinates? So we'll do this in local space. I was thinking about doing it in world space and transforming it into local space, but it was just really silly. If we transform all of our rays into local space, and we can make this plane in local space, calculate the DDX, DDY, throw that into sample grad, and that should work across all of the different ray traces. We'll just take an extra bit of ray verse plane going on. So that's how we're going to calculate the MIP level. You can go and calculate it yourself manually if you have like the texture size and stuff like this, but on the GPU it comes built in with like a sample gradient. So if we use that, we can pass in the DDX, DDY manually. So I've got this sort of shader here which takes in the visibility buffer and shades the pixels. So yeah, all we're doing is grabbing the ellipsoid index and the depth. Here we go. And then we're sort of like saying if there is an ellipsoid here, grab it, recalculate with the depth, the hit position and the hit normal and all of this, right? And yeah. Now I've got to calculate this sort of dpdx as Inigo called it. So this is a ray verse plane, I think. Like if we take like a go to his intersection stuff, we'll be able to see that it's very similar probably. Ray surface intersections, if we look for the plane one. There you go, it's a dot plus whatever this is divided by that. Yeah, dot normal. Wait. Ray origin. Oh, this has been the local space of the... Oh, no, that is the normal. It just hasn't got the plus part to it. Yeah, right. So we just want to change this basically. I wonder what that RD is. It's the ray direction minus ray direction times. Right, T is obviously the hit distance. Yeah. Okay, so what I'm thinking about doing is Yeah, we're going to just calculate this all in line, and then I'll move it into the calculate surface color, which does all the material stuff. I'll change it up a bit. So let's move out here. So I've got some comments below where that was me thinking about how I could do it, but I changed my mind now. So we need to get none of this up and right stuff anymore. So we have the standard ray direction. Now we have the ray direction that's one to the right and one up. So we have two different ray directions there. Hey there, Captain Chica. Welcome, sir. How you doing? So those in view space, then we've got them in world space. Now I need to calculate them in local space as well. So I need to perform such an ellipsoid from world. So ray direction right, okay, I need to move all three of them through. So ray direction, local space, then the one which is to the right, which is the X one, and one which is up, which is the Y one. So they're all in local space now. And now I have to calculate the difference between the two hit positions in the local space of the object. And then we've got to get into texture space, which shouldn't be too hard. So I think what Inigo used in his blog is RDX is our ray direction local space X. Well, his one is in world space, but same thing, yeah. So his RD is obviously ray direction. So right. So I think we can pre-calculate that, I think. So the normal will be hit normal local space. We could just put it all on one line. Yeah, so I'm gonna do like a dot. In ray direction, which would be ray direction local space. In our case, the normal is hit normal local space. Now we're just got to work out the Right, now we've got to make all these happen in the right order and everything. Right, I'm missing these. It's ray direction, local space X. Ray direction, local space Y. Okay. So this is a vector, and so is the other one. So it's a mole, one of them. And then after we've multiplied those two, it's a divide. And then a subtract. So divide, subtract. We'll probably move this. We'll probably make them into separate variables later on, make it more readable. Right, this final one is scaled by the hit depth. Pretty sure that is. What's T? Yeah. So -s by a single scalar, which will then that'll be just depth, isn't it? Right, so that should have calculated the difference between, so we've got a ray which goes and hits the sphere's surface. We then sort of have this plane here that we then do 2 more tests against, which is these two here. And it's calculating the ones for the neighboring pixels, 1 to the right and 1 to the pixel above. Right, so 1 to the pixel to the right and 1 to the pixel above. Yep. And we're doing that in the local space of the sphere. So obviously it could be an ellipsoid in world space, but it's a sphere in local space of the ellipsoid, right? And that'll get us the difference between those two positions in local space between pixels right and pixel above. Now we can use those to, we've now got to take those into texture space. Now the way our textures work at the moment is that we have one octahedral mapped texture, right? So that's the material cache there. This is our one that we're procedurally making at the moment, but it's it was some other texture with noise, but we've got the debug view on at the moment. So this is the octahedral texture, right? It's an octahedron, and then you're mapping a sphere to the octahedron, and that octahedron is laid out in onto a 2D plane. So these are the faces at the back, and these 4 faces are the faces at the front. So here they are here, right, the front ones. They're at the edges, and the other ones around the back. So the thing that we have to be aware about is that we basically have a texture that represents the whole 360 degrees. You take a normal of this on the surface and you map it into this 2D coordinate space. So if we have, so you can think of this plane as being able to basically, well, that went a bit too far there. You can think of this plane as effectively being able to see half of the sphere, right? So what you can imagine is this is half of the texture, right? So you can imagine that local space, the difference in local space, the difference between the pixels in local space is half the amount in a full texture. So you need to multiply it by 2, and you'll need to somehow, like, it's in the local space of the sphere at the moment. So you need to kind of, like, these offsets, we need to somehow, like, get these differences in local space hit positions and project them across the plane and then multiply by 2 or something. I can make a solid argument for any object based on plane mathematical pyramids should have some void space in texture. I'm trying to understand what that means. I could make a solid argument that any object based on plane mathematical pyramids. Oh, okay, yeah. Should have some void space in texture. What do you mean by void space in texture? I understand the first half of that. So, I wonder... See, there's actually another problem as well with my current code. Let's solve that. So this plane isn't actually offset from the center. Is it? Oh, no, it might be. Yeah, no, it might be okay. We'll give it a go. See, now I've got... Basically, it should map to a vec 0000, right? I don't understand what you're saying here. So, a sort of argument that an object based on a plane mathematical pyramid should have some void space in texture. What's that? What does that mean? No, I'm not sure of the statement you're making. Okay, so maybe we can draw these, move them back out to local space. Yeah, but the thing is they're so damn small, they're a pixel difference. Yeah, so I wonder... I think that's their hit in local space. We could bring them out into world space. And then spawn some other object on them or something to debug them. It's probably a wise idea. So that'd just be a vector at this point, wouldn't it? Yeah, so I understand how that's working. So we've got sort of doing a dot product with the ray direction and the normal of the surface. And okay, it's multiplied with the... Is that what it was doing? Yeah, and then a divide. So it's very similar to the plane, ray versus plane. It's a more specialized version of that. Ray origin, ray direction. So in this case, not really origin. Okay. Okay. Yes, that code should be right. So where we go to next? So we've got to somehow take it into texture space. So we've essentially got the hit position, the two derivatives. So the hit position, the two derivatives in the local space of the sphere. Now we have to take that into texture space somehow. We're thinking about treating the whole plane as kind of as the texture, or half of the texture. So now we just essentially got to kind of rotate it in a sense, or maybe, you know what I mean. Somehow, yeah, just straighten this up a bit basically, such that the plane will be like this and our points are in XY, along the XY. So it's got to figure out how to do that. So to draw the simplest of pyramids, you need 4 vertices. Yeah. And an anchor point. And since most 3D models have some sort of normals when it comes to 3D space, but since it's basically impossible to flatten pyramids, after octahedral, you would need 2 textures per pyramid. Unless you map a 2D plane. To color of 0, 0, 0, right? Then you pick the nearest texture coordinate plus some compensation value to get a correct texture color. Yeah, still don't quite follow here. Yeah. Basically impossible to flatten pyramids, right? And the octahedral is like, you know, a 2-sided pyramid, right? But yeah, I don't know. I'm not too good at my geometry, to be honest, so I don't really follow exactly. So what's the next thing to do, eh? So we've got to somehow get this into the space of this plane. Right, we have the normal of the plane. And we also have the two derivatives, which can kind of give us directions. So in a sense, that's given us a matrix, right? But that's a matrix that goes into that space, so you have to kind of invert it the other way around. Maybe. Yeah, what we would like is the Y to represent the up. And the X to be going across kind of thing. Actually, would we care about that? Yeah, no, we need it as a 2D vector. Yeah, so I guess our thing is like, how do we project so we've essentially got 2 points on a plane. How do we get them in the plane space, basically? How do we go? It's a subtraction based on the center position, isn't it? Is that what we're looking for? So from the hip position, so it might be as simple as this. So you got some sort of like plane. Imagine you got like some plane. You've got a ray which has gone and hit here. We've gone and hit to the right and up. And in order to get no, but we did a well, we've already got them as a difference, isn't it? Yeah. But we need to get it. We've already got it as a vector, basically. But we want to sort of orientate them such that they are in 2D. They're 2D again. So I wonder if we can try and find out by searching for sort of ray versus plane, find XY on plane, something like that. Finding out XY coordinates where Y intersects 0. We want to sort of transform as the local space of the plane somehow. Hmm. That's just a reverse plane intersection. So what I want is like I've got a coordinate on that plane, but it's not. It's in. It's not in the local space of the plane. It's in a different space. So I could get my. I think it's just got to be a matrix multiply, but I wonder if there's a simpler way to do it. Probably break the matrix multiply down, and you've got the normal. You've also got the 2. You can normalize the differences, and that gets you your basis vectors. Maybe we'll have to do it that way. Let's just cheese it for a sec. So you're gonna get your 3 basis vectors, right? You're gonna get your right, which would be normalize dp dx ls local space. So that'd be your up. And then you've got your file. Also, it's like basis x, basis y, basis z. So that is just that is your normal, the hit normal. So with those, you've got yourself a 3x3 matrix, right? But you want it to be inverted. So that's right. Maybe we could make a. Let's go to my math stuff for a sec. So we've got quaternion. Like. So you can get a. Right, look at quaternion. What was that? Yeah, so you can produce this quaternion, then you can invert it just by doing a minus, basically, quite easy. So that is. So forward and up. Then it would do one of those if statements, basically, right? And then return. And then it's just a multiply vector after that, so it's just that. Well, the alternative is to use a full-on matrix. So you just compute the. Oh, here it is. Yeah, then you do the inverse code for the matrix, which is probably better. And then do the matrix multiply. I guess so, but there must be a better way to do this. Because this matrix would be, the matrix that you get would be the. Yeah, the local space from plane matrix, basically, wouldn't it? See, I wonder how he does it. He's done it in this sort of shader. Why did he do it? It's got a shaded toy example here. Yeah, he's throwing it straight into a cube map. Hmm. Yeah, it's just throwing it straight into a cube map. Right, let's just take our basis vectors and produce some form of matrix. So this would be basically how do you get into local space from plane. Transform. So say yeah, wrong one. It's a matrix I need. So the basis vectors, so basis x, y and z. And then you obviously have translation of 0, all of the things. And then you can invert that, which is I don't really want to be doing these things for every material shading, but let's just get it working. Plane from local space equals inverse local space from plane. Then, all we care about is the rotation, really. Yeah, I wonder if the quaternion would be better. Do you do much low-level programming in your day job? Yeah, I would say do mostly all the time thinking about that sort of stuff. Yeah, we do program in C++ at work, so we do a lot of, well, depends what you define as low level, right? But yeah, it kind of varies a lot day to day, but it just depends. Sometimes you're doing some really sort of like platform code to do the engine, or other times debugging stuff, so yeah, I work in C++. So yeah, I would say yes. Use a lot of CPP crap, or do you keep mostly C at work? Well, so it's kind of like, it's a bit of a weird one. So there's some people that really just like kind of C style, and there's some people which like proper OOP style. And there's some people which like the sort of C with classes style, that sort of like game, in the game industry, the sort of like C with classes that people typically do. It's like they just put everything in methods and classes, but it's very much no inheritance or anything like that. I'm obviously very much on the C side of things. But yeah. But unfortunately, there is probably quite a lot of people who like the OOP side of things as well. So yeah, it's one of them. People go through school and they can't unlearn OOP. So, yeah. My laptop decided to lose internet connection, so I cannot use this thing anymore for the rest of the stream. I'll just have to check out here. When having the dot operator is a syntactic sugar. Yeah, it's syntax sugar when you're typing it, but it's not syntax sugar when you're trying to decode what the crap is going on. It's, you know, you can barely find stuff in the code base when you got 50 odd functions called in it. And it's like, for crying out loud. You press F12 and Visual Studio just struggles. So, yeah. Yeah, I think you can then just like basically generate this sort of dpdx in plain space, which would just be sort of like a molv on the dpdxls local space. Oh, for crying out loud, it's this plain from. This is a bit much. You need to do the Y version. And then what else can you get? Yes, that's it in plain space. So now that you got it in plain space, imagine this plane represents half the texture. So in order to get into a full texture, you need to multiply it by 2. So you get it in texture space now. In UV space. It's not UV, is it? Texture space. Multiply scalar. .5 or 2, yeah, something like that. And then I think that's it basically. That's your ddx, ddy. Ta-da! So I'm gonna try this out. We've got to bring back. Got to get it compiling and bring back the proper texture. And then we can figure out like if there's a way to do it better. But hang on a minute. If you're in the local space of the, you've just applied a rotation. So local space has a radius of 1. Is signed norm. So that means it has a diameter of 2. So yes, half dimensions of 1, right? So do you need to times it by 2 at this point? I guess the simplest thing would to say if you had a sphere, here's the plane that goes over it. Just bring it down to the basics. You only have 2 pixels, unfortunately. No, maybe you gotta say 3 pixels. Make it make more sense. You've hit this one. You test that one to the right and that one up there. And you've got the difference between those, right? Oh, it was Wowhead. Yeah, I never really knew WoW when it was at launch. I knew about it afterwards, so I don't really know, but I know it was a very hyped game when people were playing it at the beginning. Yeah, maybe. Games will maybe get good again one day. I guess people maybe have had moments like that since then. Maybe. Yeah, I guess some of the games these days, they have the hype, but then they don't live up to the hype. So you'll get it, and then it's like busted on launch or something. And then it doesn't have half, has half the content that you thought would be in it or something. So you got those 2 differences. And yeah, so if that's half the texture, here is half the texture, you times. But you can imagine the sphere. You can imagine in a sense there's another half of the texture. Or another back piece. So it's probably not really a whole times by 2. So you times by 2 across each dimension. You will get a lot more areas, so it's probably a quarter. So yeah, who knows? Okay. Hmm. So right. So this will be essentially like no, I think it is. So we're using the octahedral map, and one side of the sphere would be represented, I guess, with half. Yeah, it's half of the pixels, isn't it? It is. It is. It is. So would you times it by 2, or would you divide it? So yes, I should divide by 2. Yeah, because imagine if this plane represents the whole texture, these need to be halved in order to fit the other side of the sphere on. Right, okay. That's good. Okay. So I think that's right now. So we just gotta... The problem is these need to say .xy now, I think. Now, the thing I want to be careful about is maybe we don't get the X and Y. Yeah, maybe the matrix I've made doesn't rotate it so that it's perfectly on along the XY plane. I also complain about here. Doing a float doesn't implicitly cast to. Oh, right, okay. Which means I forgot to do it here as well. And that's an S sub. I don't know. So. Cool. So these are 2's there. Right, these were the wrong inputs in plain space. Okay, so I think we're going to get something running now. So we've got to get the other texture back on. Right, we're seeing some sort of like edge there, to be honest. We've got seeing some boundary there. I wonder if we see the boundaries here. Anyway. Okay, so the other thing we want to do now is go to that test material that we're making and actually put down that sort of noise. That sort of noise on top of it. So we can see some sort of, well, that's not it, is it? But yeah, so it's the smoother version, but we want the noise on top. Ah, the noise has been commented out. There we go, let's put that noise on there. So now we should see some sort of high frequency information on in the high resolution textures, obviously. And then we should hopefully not have that interfering with the stuff at the back. That seems alright. Okay, I'm moving and this is not... It seems to be selecting the right MIP level, although I would be very skeptical of it. Because... The edges definitely seem a bit messed, but that's probably to do with the anti-aliasing, actually. Yeah, it's the anti-aliasing messing up. So it seems like it's okay. This seems like it's selecting the right MIP level. Now we don't know what it's selecting because we haven't seen any feedback or debugged any of our variables. But if I were to hard code this, you would see this sort of, we'll be sampling too much of a small area for the pixels which is shading that area. And you would get that high frequency noise show it like just skipping a whole bunch, and this is not what I wanted to view, this one. So you'll see here, if you sample the wrong MIP level, you'll get a 2x2 in this MIP level, and you'll be going across this noise. But your pixels might be actually larger in area, that in screen space. And what you really want to be doing is sampling from a 2x2 in a lower resolution, such that you get an averaged out. You get an averaged out version of all the pixels that were in this area. And it's as if you're doing essentially sampling this whole big area, then taking the average, but it's pre-calculated as in the MIP level texture, right? So if I were to write a bit of code which basically says, hey, if time U32 graphics global Thank you, Perron. Appreciate it. Yeah, I'm just writing a sort of a from scratch renderer using ray tracing. Well, ray tracing in a compute shader, but it's not anything like hardware ray tracing. And we are essentially just trying to make something unique looking. And right now I'm doing materials. So this is kind of like where we start to look at how things, how we can sort of like texture things and how we can give them detail. And yeah, this is going to be a bit of, I think we're going to have a couple of streams of like testing out, like, right, we've made this really nice material. Now we're going to repeat these spheres and make a surface and see how that looks, and see if there's any sort of problems with the looks and what we can do to fix it. And after we've done all this material work, we'll be building a model editor which allows us to make models out of ellipsoids and things. So we're really defining how a sort of a very sort of custom looking game. But yeah, there has been a few games which, I think there's only been one game that I've known, but it's probably been more which use sort of like spheres and ellipsoids, but they're not really the easiest things to use or to make look good, I think. So we're going to have some challenges, but I got some ideas. So if the time, let's mod it with, let's do 8. So every like 4 seconds, we'll just do a 0 in this DDX DDY. So this will mean, hey, always use MIP level 0, which is the highest resolution. So you'll see it will sort of jump. Oh my days. Hang on a minute. The vector 2s, obviously. So they'll really jump around. Let's get in there. There we go. We're seeing it. Can you see how much those pixels at the back move? Oh my days. Sorry, I bugged that one up. So you watch this surface here. See here how you see that high frequency noise that you see on the left hand side here. Right, it just appears and we're seeing the high frequency noise when we move. It really moves so fast over such a small area and glitches about. Now when it works fine, that's because we've selected the right MIP level and we're sampling from a lower resolution texture which averages out all of that high frequency noise and gives us a nice smoother looking sphere we're looking at. But when we get closer to it, you'll notice that it has the same high frequency noise. Right, when we get there, you know, every 4 seconds it's changing the way it does the thing. And here we go, wait for it, high frequency noise, bam. Cool. So it seems like we are selecting the MIP level correctly, although I have got an issue with the fact that we're inversing a matrix. You know, it's quite a bit to do this, and you know, I need to double check, right? Is this actually, when we transform into the local space of the plane, is it actually 0 on the Z? So we're going to go ahead and produce 2 variables called A and B. And I'm going to literally just say if is mouse at, right? So I got this lovely if statement where I can just pass in a pixel coordinate of our mouse is at that pixel coordinate. Now we can go for ham and print A and B out. But it's classic C, we got to type out manually, but this is the way. So a.x.a.y.a.z, and then basically just replace those A's with B's, and then we're done. So what we're looking out for is that the Z value is 0. And then that means we should be calculating the proper xy values. So if I hover over here, right, they do have a z value of 0, but they also have an... Yeah, that's it. That's it. Look at that. And they obviously have a y as 0 as well. Right, so if the x... So this is where it's just like, did I need to do the matrix transform to get its local space of the plane? Like, how can I somehow... Like, I just need... I don't need them rotate perfectly like this. It's maybe a bit overkill. I just need a way. Let's get that music back. So let's go to the drawing again. I've got this plane up here. I've shot 3 rays against it basically. You've got 3 different pixel coordinates, right? Sorry, 3 different hip positions. This is the main one. These are the one's the right one up. And we've got the difference between these, right? And that's what ddx dy basically is, but this is in the local space of the sphere at this point in time. And we need to get those into the local space of the plane at least, or kind of like, we just need them across 2 dimensions. So how do we get them across? How do we project? How do we get the point? Project points onto plane. What I kind of want, isn't it? Multiply the unit vector by the distance and subtract the vector from your point. I want just a 2D coordinate. Is that what it's called, projecting? There you go, projecting 3D points onto a 2D coordinate system of a plane. To get 3D points, 2D coordinates, you first need to determine the 2D coordinate which is contained in your plane. You need to find the basis vectors EX and EY in your coordinate frame. So technically, if you normalize the DDX or dpdx local space and the Y one, that's already those 2 vectors. First, you need to find your basis vector EX. For this, you can choose any unit vector. And is contained in your plane orthogonal to the normal. Yeah. That's good. So we've already got that. We've already got this. We denote P as the projection of the arbitrary point onto our plane. Oh yeah, what was R again? One possibility would define your basis, your first basis vector via oh, and then I want to tell what R is now. What is R? What have you done? Yeah, C game dev. You see. Is SR referring to the point S and point R in the sense of... Right, so it seems like it's maybe got a point R. Arbitrary point P to define onto the defined plane in 3D. Oh, so is that a relative point? We can then define a 3D vector denoting the distance of point P to the origin of the new coordinate system by that. Okay, great. So that's just the relative position, which we've already got. That's what these are. These are relative positions from that center one. To get the 2D coordinates for the point, we simply project the 3D vector of P onto our derived 3D vectors. Right, so it's just the dot product. Wait, the scalar product. Yeah, so you got your two basis vectors, of course, right? So it's just a dot product that gets you yeah, but the things that we're projecting are okay. Right. Yeah, okay. So you get your two bases, and maybe it's just a simple case of saying your sort of dp dx in plane space might be as simple as saying it is right. So the x is always going to have a 0 for y, I think. So what is the scalar product? It's the dot product. Perfect. Good. This makes a lot of sense. Right, I'm just going to go and help my wife with something. I'll be back in a couple of minutes. She wants a little bit of help. Hello everybody, welcome back. How's it going? Yeah, so we're just doing this thing here where we're trying to make a cheaper way of calculating the point on the plane, basically, rather than making the whole damn matrix, inversing it and multiplying with that. We can just use the dot product here. So the thing is our basis vectors are just the things we're using the dot products with anyway. So like so why is it going to go nothing like that in that direct? Yeah, here's the thing, right? You've got your sort of plane. You got that hit point there. You got another one to the right, another one to the top. You got these differences vectors, right? And obviously when you dot x across the x, we might just be able to shortcut it and just use the length, basically. Something like that. So obviously when you try and do a dot product with the normalized vector of this one, so the normalized one might go out like this long, right? But you're saying like how much does this project across this? And it gives you a sort of a length, doesn't it, right? Yeah. But obviously this perpendicular vector is not going to project across that at all in any way. So the y would always be 0. So what we're really looking at doing is just taking like a simplified version of this, is just take the length of this and then cram that in the x, whack a 0 on there, then you put a 0 here, then you put that in the y, right? So it's one square root operation each, right? The norm is just basically a length op, and then multiplying it by that length. Yeah. So that's just reciprocal square root, isn't it? Yeah. So normalize is just a length, and then you divide the result, the length, on the vector you're trying to normalize. And then, so we've got rid of those normalizations now, and just put them there like that. Now, so that's in the plane space. So I like that, it's simplified it a lot. So now we don't need all of this matrix stuff. And right, we can prove we could have proved it was the same. Yeah, should we prove it's the same? Let's put a 2 on the end. And then let's go ahead and do xy right, dp dx ps2 dot, and then we want to do the y version dot y, right? So what we're looking at is we're making sure, right? Now that would have been 0. Sorry, yeah, that would have been 0. Okay. Let's just make two vectors here. It doesn't make any sense. But yeah, we've got A, X, Y, B, X, Y. And they've just got to be identical. And if they're not, then the code is obviously the way we solved it is not the same. Sorry, it doesn't produce the same result if they're obviously different, and therefore we've got to figure out a different way of doing it. Well, there's a problem with it. Okay. Right. So we're going to hover over a sphere and then see those values. We get printed out from the shader. There we go. So I'll leave it still. So there in the lower left, there's an A, which is 0.074325, and on the B side, that is the same. Then the other one is 0.077124, and it is the same on the other one as well. So that's good. So we're getting the same values without doing all of the crazy amount of work where we... So the normalized here was already more expensive than doing this because it's an extra couple of multipliers. And then it was doing an inverse matrix and then a matrix multiplier to get those. So that's that all simplified. Good, good, good. And then it's just a case of getting it in texture space. Now this, so that this is in plane space, this is texture space, and this is like a best guess. So we just half it because you only have half the space visible from a direction. From the camera's direction, you have only half the sphere that's actually visible, and a texture actually represents the whole sphere because we're using the octahedral mapping. So that would mean we need to sort of half our dpdx in plane space to make it roughly what it would be in texture space. Just a best guess. It's not perfect by any means. So that's good. So apparently we've done that. Now, so this will work across all of my different ray tracers, because all I have to do is have a hit normal, and I can do all of this extra maths basically to... We should really write a comment down. Yeah, what we need to do is have some rays which go into the neighboring, through the neighboring pixels, test against a rayverse plane, and get the difference between the ray hit position and the neighboring hit positions. That's what this is, a difference between those. Then move them into plane space, into texture space, and then that's our ddx, ddy, which we can use in the sample MIP gradient as the ddx, ddy in there, and that will select the right MIP level. Cool, so now that we've got that done and it seems efficient, we're going to move it into the... We're going to move all that plane calculation stuff into the actual material shading function. And that way, see here how we've got this sort of like high frequency noise here, but in the background when we're moving around, we're not seeing that high frequency noise, it's just an average of that high frequency noise. You know, it's just standard MIP level stuff, but it's working out fine, which is great, it's what you want. So I want to quickly just move a lot of this stuff inside, like we'll pass some of them as input parameters, but this is definitely going in there, so I don't have to keep redoing it. And then, yeah, but we might pass in the neighboring ray directions and stuff. And then we can get the rest of them working with this. And then I would like to prepare for next stream where we make a couple of materials. I'm going to keep it 100. We want to debug this code. Okay. Yeah, debugging shaders is difficult. That's why I've built my printing and ways to also draw debug shapes from shaders. And so I can sort of just debug any data I want, really, which is quite nice. But yeah, there's no breakpoints, unfortunately. So all we have to do now is drag all of this into this calc surface color. We're going to calculate the ddx, ddy. Yeah, so on the mall in local space, so I guess I could call it, so dpdx, we'll rename it a bit. Nice. So we're not going to have shading dot dd, so we just have dd. Rightio, and then in shading, we're going to instead now have a bunch of little vectors come in. So this would be the ray direction. Local space across the x, or it's the neighboring one, right? So they'll be coming in here. So all of these guys will be shading dot. We have the hit normal, right? Oh, we didn't have the hit normal local space. We get that in here as well. Bit long, not gonna lie. Yeah, maybe I can shorten these variables out a bit. A bit damn long. So RDX maybe RDX. Let's undo all that briefly. RDX. So that's shading dot ray direction. That is RDY. Then it just RD. Then we need normal local space. So this is RDX, RDY, RD, and then normal local space, and then we'll also need the depth as well. The sort of the hit. What is the depth along the ray that you hit? I guess we'll just call it depth. Cool. So another one would be we need some depth. So let's go back to shading. So I'd also need the local space one back in. No UV, passed in manually, that's not a thing. And we would need depth. So a single scalar of depth. Nice. Okay. Why ain't that working? Surface normal. Okay, good. Right. So now what we need to do is make sure that all of the other ray tracers use this calculate surface color. So yeah, they pass in all the right parameters. And then that means they will calculate the right MIP level. So let's go over all those quickly. What's this one here? This is the BVH ray tracer. We skip that one. It's dead code. So we need to pass in the hit normal local space. We need to pass in the shading dot ray direction local space, which we haven't got anymore here. We need the one across the X, one across the Y. This one's the super sampled anti-aliasing. What would you do for that one? So you're getting a super sampling already. So you want to use the MIP level, which is like you want to be doing it the super sampled dims. So that's like twice or 4 times or whatever the resolution. Oh, let's find that one. Right, so these guys here, let's grab that, go back here. Right, so you want to be doing the super sampled dim, so it's a bit different. Super samples, anti-aliasing, screen dims, and pixel dims. Now we obviously want to produce the neighboring rays in world space as well. Then when you've done it, got it in world space, you can then bring it into local space. So here we do the material shading inside the super sampled anti-aliasing. Go over all the hits. Yeah, then we do the expensive shading one by one. So plop those in there like that. So we take the world space ray directions and move them into... Did I really transform those as points? That was wrong. Oh my days, so... I was running on it with incorrect code. That's scary. Alright, we'll look at that again later. Shading dot depth equals hit depth. And I think that was all the new ones. Yeah. So we'll do that again for the other 2 ray tracers. So we've got another one which is multi-sampled anti-aliasing. So we're going to go ahead and find that one. So multi-sample anti-aliasing is the next one. So calculate surface color. Right, so for all the hits that we've got, we need to get the ray, here. The ray direction and the neighboring ray direction. Then we also want to bring those into local space. Bring those into local space. And then fill in all the extra shading parameters. So the surface normal and the different ray directions and the hit depth, and with all that, we can calculate the ddx dy correctly, no problemo. Then there's another ray tracer, which is the ray trace anti-aliasing, which is another one I sort of made up. Do you have an idea in your head how it's done in other engines and try and reflect on that to code functions? Yeah, so that's a good question. You know, a lot of people will, look at how another engine does it and it's like, well, that's what we need to do. But really what you should really try and do is there's really tons of ways to solve a problem. And you need to look at what other people do for inspiration. And so when it comes to what other engines do, it's like, well, they're obviously trying to solve it in the more general case for tons of other people to use. So for this game, whatever, there are obviously lots of things that we do similar within a PBR pipeline. And you have a concept of a model and a model instance type of thing. So there are concepts which obviously are very similar. But yeah, it's always good just to take a look and see what other people do and get inspired and be like, oh, it makes you think about things in a different way that you wasn't quite thinking before. And then you can use that to sort of fuel your future ideas, basically. You will have to let them sit sometimes or think about them in more detail. But yeah, I don't necessarily look into other engine code. I more look into sort of pieces of information online, like some docs, or maybe someone's done a video on something. I don't really play around with other engines. So is this the ray trace anti-aliasing one? No, it's the visibility buffer approach. Right, RTAA is the final one. Okay. So we're adding in those different ray directions. And then we're adding in we're going to do the shading, which is here, different local space. And then fill in the different shading params. Then we'll test it one more time, and then we'll prepare for the next stream by getting we're preparing for writing our own custom materials. Oh crap, it is using UV, why is it doing that? Right, yeah, you got the hit normal pack octahedral. Yeah, I don't need that anymore. I'm passing in the hit normal. Oh, we missed the surface normal on that one. Right, the final one here also needs... Right, so we're taking that sort of like packed... Okay, so we did miss one thing, and that is we do need the UV, but we get that from the hit normal in local space. So we take the normal of the sphere in local space and map that into an octahedral 2D map. Okay. Right, so hopefully that should all work again. We're going to test out all the different ray tracers we've got now. Right, what is this complaining about? Four, 7, 1, 5. Oh, I put that in a global for some reason. What a lolly. The parameter called E. The missing E. Damn it, I used to pass in the ellipsoid index at this point, but then I got rid of it. Right, so E index. Let's pack that in. E mask. Is this the ellipsoid index? Now to get the ellipsoid, it's just... Oh. E index, so that when we pack that in. Right, then to get E, it's just reading from the buffer again. And voila, so the material, which was material index, is E.material index. Cool. Oh no, what is that missing? Here, normal local space. Why don't I have one of you in here? Oh, I do. It's called the closest hit. Bit of a terrible name. Hit depth. Is that just depth here? Why don't I see any depths? The hit list of depth hit depths. Ah, there it is. Good, good, good. So hit depth. Nice. Right, that should be it. So now, oh. Okay, different shader now. Right, it's just called depth. Let's go. So now we'll test out the other ray tracers. We'll switch between them and make sure they're... Right, so that looks alright. We get up close, we're seeing all the detail there, which is good. I could hop open the texture viewer and take a look at the scene. Bring the color down a bit, or the white down a bit, so we can actually see some at the right levels. We zoom in. You know, it's nice and pixelated there, although it's getting a bit blurrier up here. Maybe that's just to do with the lighting, I'm not sure. Seems alright. We can sort of move the scene a bit closer. You already start seeing it more there now, right? And as you zoom out. The detail is slowly disappearing and gone. That's alright, I guess, does the job. Okay, so the next thing to check out, that's just the visibility buffer approach. And as you can tell, we're moving this background here and it's not, moving the one in the background and it's not, you're not seeing this high frequency noise there at all. The next one to look at would be the, so if I okay, I've not really properly named this. So if I turn it to heat map mode, that will bring back the original ray tracers that I've got. And you can tell because it's rendering with a transparent path. So this supports transparency and everything like that. And we're going to be using these ones. Actually, I'm just currently using the visibility buffer approach because I tried it out and I tried it out seriously and I don't think it's going to be possible, but I just haven't bothered changing the code back. So this is the ray trace anti-aliasing one, and we should be able to see when we move, we're getting the same effects, right? It seems to be working fine. Well, we are getting stretching on the, that's interesting. Oh, this is where the noise, yeah, the way the noise was generated, that's okay. That's just me making a terrible noise texture. Now the other one was, if we switch to multi-sampled anti-aliasing, it's obviously slower, but yeah, that one happens as well. Then super sampled, that one seems to be working fine as well. We're not seeing any jumpy pixels in the background sphere there when we move. That's great. Right, so I'm glad we've got that sorted out today. I'm going to commit that when we're done today. But so in the next streams, so the plan now is like, okay, so we've got the material caching stuff in, we're able to stream in materials, right? And we're able to also shade pixels in on a sphere by sampling from a material with a 4 MIP chain on, and we're selecting the right MIP level. So that's pretty incredible. So the next thing now is that we need to make sure that the route we're going down is good. So I want to spend the next so many streams, however long it will take. Might take 2, might take 3 streams. Might take another couple. But we want to make some really nice looking textures. I want to make a few of them. I think we'll have a bit of fun today and try and figure out which ones we want to make. So I've got like a materials plan here. You know, things don't always go to plan. I'm going to have to rewrite some of this maybe, but it's good that you write plans out. You're able to think about stuff a lot more. So I've got a list down here. These are the ones that I've got right now. It's like a bark wood texture, like a planks texture, and like a volcanic ground texture. So I want to make something like this. So I guess today let's set up an environment such that when I save my shaders file, so maybe I can quickly throw this in. into the game code. If my shaders file changes, rerun the compiler, and then the game is going to automatically reload the shader in. So I've already got the hot code reload working. When I usually stream, I'm so curious about this stuff. It's like magic to me, never done engine. Yeah, so I stream. There is a timetable on Twitch, but it is Tuesday, Thursday, Sunday. So I stream. So yeah, 2 hours ago. Basically, I start on Tuesdays and Thursdays, and then I start 3.5 hours ago. Right, in your time zone, which is about 6 for me. GMT +1. Yeah, on Sunday. So I start a little bit early on Sunday, basically. What sort of stuff are you doing at the moment, Peron? Sorry. Payon. Maybe is pronounced it. Right, so yeah, so I think let's just quickly jam in. So I've already done hot code reload, but I haven't. So I got all the sort of back end stuff done for that, but it only picks up when the shader file is reloaded. So the compiled shader is reloaded, but not the source code. So why don't we cram in like a thing is if I put the source code changes in, then right, GPU.c, there's like a shader, like a timestamp, isn't it? Yeah, I'm currently doing it with timestamps. It's a bit dumb, but there we go. So I could do a very simple thing. We're in my main loop. Very terrible code. Just don't mind me. So the path is going to be code slash graphics slash graphic shaders.c. If that changes, dot seconds equals 0 and equals 0, then we'll just set this up as equal to new modified time. Okay, so you're 1 hour ahead of me. Right. Yeah, so it's probably, yeah. So I probably start 8:30 your time, and then I start on Tuesdays, Thursdays, and then 7 o'clock p.m. your time on a Sunday. Yeah, so we're saying if they are now different, then run that build script command, which I'm just going to cheese in there. Now I only really want to do this for screw it. Right. And then that'll recompile, and then that should trigger the other one. Yes, the problem is I'm doing it with timestamps, and like the timestamp changes when something has just modified it, but not finished modifying it. So it's so annoying. I think you can do it with like system. You can do it with like notifications from the OS, and yeah, it's just code I didn't have access to, so I just did the easiest thing. So now let's try. Crap, I think it's continuously reloading. Yeah, I didn't update the thing, did I? Alright, let's try this out. So it might reload right away, which I hoped it wouldn't have, but... Because I don't want it to... Missing texture. It keeps continuously reloading the system. Why did it fail to execute Spear VOps? What are you talking about? What you talking about, mate? So, last modified date, new modified date. If it's zero initialized, just give it the latest one for now. Oh, it's less than or equal to. Don't do this to me. Wait. If it's less than. Oh, my other one's continuously loading. Oh, less than or equal to, then it's continuous, isn't it? Damn it. Right, it's greater than. Oh, man, I was... Damn Boolean logic. Okay, so that shouldn't fire off the first frame now. So let's try and modify some code. So I right click, I can probably keep that above the others, right? And now we can change the texture that we're generating for this. So we'll hop into shaders.c, we'll hop down to here. We'll enable this line here, then turn the gradient off. Or sorry, the noise generation. And that will bring back the debug view for the octahedral map. Oh wait, I did change it. I did just save it, right? Oh, it's still just running. I wonder if alright, can I split that to the side so I can come out. Alright, it's rocket science. So as to save that, do we see this change? No. This exit was some weird error code. So if we rerun that, So yeah, it's got this silly texture now. So let's go and try and put the better texture back. So we save it. Does it exit the program? No. Oh, it's because my... Okay. That's great. Another reason why. The path to the file is wrong. It's in modules. Yeah, I removed the engine folder now. We just don't have the separation between engine and game anymore. Because it's a hard distinction to make sometimes, so I just not bother making it anymore. Right, so now I'm going to put back in that debug view, so hopefully when we save it, put this above all of the other ones. Here we go. Does this texture change when we save the file? Right, it closed the program like I told it to. So let's try that again. Stupid thing. Right, here we go, finally. So yeah, we're basically running the compiler again when the timestamp changes. We are then running, after the timestamp changes for the SPIVy file, we're then reloading everything into the Vulkan layer. Or recompile all the pipelines and that. That was done in the past stream. I expect that this to be doing something and... Alright, let's try that again then. Print out yes. I could have done a message box maybe. Okay, hang on a minute. Right, 1 for the noise. This multiplies everything by 1. Then it's this signed thing, so we... Okay, we've got the yes popping up. So it seems like it ran the program. Can I look out for that yes? And see what else printed out? It's the terminal. It might have got some other error. There's nothing else in standard out. It's a bit weird. But it's definitely running this. So what is the timestamp for those shaders? Just now. You're nice. Oh, not alias to that, yeah. Yeah, it's 43. Just 1 minute ago. So in the GPU case, I guess we can pop up the message box. reloading spivvy file. And this message box will be recompiling shaders. Let's try that out. So we should see two message boxes. So go to shaders. So one message box. Two message box. What? Oh, is this not getting regenerated every frame anymore? So maybe it is working. Let's change the encode to surface. We'll change color dot R to 1. So we always will output some form of red. Recompiling shaders. Okay, so it is working. It's just the test material isn't plugged in. That's cool. All right, progress. Very good. Okay. So I'm not running test material every frame like I was doing before. So we move that into a place where it's running it every frame. Then we'll be prepared for next stream when we make our own. We'll be changing this to make a proper nice material. Now we'll give it a go, test out what we're planning on doing for the future. So test material. Right now this only runs at frame start. We're going to move it, or copy it actually. For the frame start that gets called every single frame, not the start of the game. So there's another one which happens at the start of the game. This one happens for the rest of the game. So I'll just run it here every single time. Which means now when we hot reload, or when we save, we'll be able to, it'll be hot reloading. And this is the workflow we'll be having next stream. So we'll have this open here like so. Right, I guess we probably just do that. And then we can do this or something, right? And then we can just like change some shader code. And then do that. This wouldn't actually happen. I should remove these. But then voila, it would change, right? No? Oh, it's because the textures are not... Nah. There's another thing that needs to change. Right, let's commit this code we've got now, because this change I want to make is going to be breaking. And I want to make sure I don't commit this change. Right, so what have we done here? Oh, I've not committed that as well in HCC, have I? Yeah. Right, git commit. So we've got texture. Calculate surface color. Yeah, so we could say like basically proper MIP level sample materials with correct MIP level. Nice. Just tag that for today's stream, which is 25, isn't it? Is this public repo? It's kind of private, but so for those who support the channel either via Ko-Fi or via Twitch as a subscription, get access to the GitLab. There's a link here where people can, after they're subbed via Twitch or Ko-Fi, if you follow that link, it takes you to the Discord, and there's instructions on how to link your Twitch or Ko-Fi to the Discord channel, and then you will get access. There's instructions in there to download from the GitLab, basically. But yeah, Ko-Fi is much nicer for me because there's more money that gets sent my way, but either way works. I appreciate the support for everyone who's supporting the channel. Hey Brian, how's it going? Welcome, sir. How are you? Your console's a bit better today. Yes, it is actually. I've got. Yeah, hey Pete, good to see you. My yeah, much better today. I was going through on Sunday. It was kind of like in that sort of mode where you're sort of like sneezing all the time and sort of spreading it more. And then yeah, I'm in the more of just dealing with the rest of the symptoms now. I'm good. Also, good to hear. Yeah, not bad. I've actually just been a bit tired today. Didn't really have the best of sleep. Well, I had a good sleep, but I was super tired when I went to sleep, so yeah, I got sleep to catch up on. But other than that, nothing bad. Yeah. We got some sort of MIP level calculation stuff done today, which is really cool. And we've just got the hot code reloading made easier, so we can just save a file, save our shaders file and watch it reload. And we're just about to get it prepared for next stream, basically, where we can we're going to make probably a couple of, probably one texture, to be honest. We'll see how good I am at it. Procedurally, all with code. So we're just going to go to the material cache quickly and sabotage it such that it will always reload. Which is terribly bad. So to do remove me yes. So now it's always going to reload the materials. So now hopefully run this one like so. I wonder how many things can be pre-rendered. The easy thing is, these things are things that don't change, or at least should be fast enough for recompute when notice. Yeah, see, you already kind of have that, right? Like textured, like just start simple, right? Textured surfaces, that's pre-rendered. It's pre-rendered stuff, right? Sky maps, pre-rendered, or real-life photos in this case, that I took from the internet. And yeah, so rendering is already utilizing pre-rendered stuff. And then oftentimes as well, sometimes you will procedurally generate like a environment map or a sky map or whatever. And you do that procedurally in code, and that'll just be cached on the GPU, and that's all pre-rendered. Then, yeah. So yeah, pre-rendering is basically the art of how you make stuff go fast. Lighting, if you know about GI, like global illumination, basically they would bake the GI, the global illumination, into light probes, and they would ship that on disk, and then that would be right. How could reload does it work? Yes, took a bit of its time, but 2, 3, 4, 5. That's okay. I would expect it to be faster though, not gonna lie, but there we go. Yeah, these are baked light probes, but now these days they do ray tracing in real time, and because hardware's still not good enough, there's noise everywhere. And we have to deal with all that temporal artifacts. But yeah, maybe we could actually have a hybrid of pre-rendered stuff and pre-rendered light probes and dynamic light probes. I don't know. The materials thing, you mean like apply normal specs onto diffuse and advance? No, I just mean like No, I mean in terms of like, yeah, you know, textures, materials, yeah, they're pre-rendered things, right? You know, if you take a look at like a wood texture that you might sort of take and, you know, use in your game, that's pre-rendered. And you're texturing the surface with that pre-rendered thing. So games already do that. Does a 32 by 4, so vector 4 turn into YOM register? No, so I didn't do any of that stuff because it means stuff has to be aligned. But I've got a maths library that works across CPU and GPU. So it's the same thing, it's just 4 floats. Or 3 floats. So the bit that I'm concerned about is why does it take so damn long? Oh, because it waits a second each time. That's why. Yeah. So I've got a second here before my compiler kicks in, and then I've got a second before the other one kicks in, thus making it 5 seconds. It's not a good turnaround. Let's see if I can remove that second and see if it works. See if my compiler will be fine with handling a file that's half written to. Right, here we go, and 0, 1, 2, 3, 4. Okay, so we got it in 4 seconds. Obviously, because we just removed a whole second, but of sleep time. But yeah, I can't remove the other one because it will complain, I think. Does my... How long is my shader compiling taking? It's not taking seconds, is it? Let's find out. Am I using the release build? 2.4 seconds. Do you have any scatter or gather since you're not using SOA? No. No, I'm not doing any sort of SSE stuff in any way. But yeah, on GPUs, it's you know it's all using vector registers under the hood, isn't it? It's a good programming model. It's pretty fun. Yeah, I'm going to go over to my compiler for a second. And I'm first of all going to commit those changes. Right, fix sample gradient. Arguments, parameters. And I'll push that. And then I want to do I want to do one of those compiles, because I think I didn't do it as release. I must have done. But let's just double check it just in case. Alright, so we've moved that over there. Let's go back to game without an engine. And let's run that HCC command again and just time it. Right, yeah, well, it's 2.3 seconds, same thing. Yeah, so there's the exact same build of HCC there, so that's okay. So we know. That takes 2 seconds, then I guess when it tries to recompile all the shaders again as pipelines, it does take a little bit of time as well, which adds up to 4 seconds, including the 1 second of wait time. So yeah, compiling the pipelines is probably about another... Right, I'm also running a SPIR-V opt on that, isn't it? There's a SPIR-V opt which runs. So if I took out the -O, yeah, there you go. SPIR-V opt takes a lot of time. Yeah. So yeah, my compiler can end up being quite quick, I guess. I've done some really stupid stuff in it as well. But yeah, it's only outputting like SPIR-V, isn't it? So it's not shouldn't be that slow. Okay, we could imagine that it's running a shader on like 2000 cores. Yeah. Well, that's the thing. Is like RDNA, AMD RDNA hardware or whatever. When you run on like a GPU, it automatically goes into SIMD, right? Runs in, there is the ISA spec docs. You can go and read these things. But yeah, you basically have compute shaders which have Wave 32 and Wave 64 modes on AMD, but NVIDIA's Wave 32 only. So you've got 32 work items that run in lockstep together. So whenever you run a piece of shader code, like it's one instruction at a time, whatever it compiles down into. But you can think of each of them running exactly at the same time across 32 threads. But it's not really threads, it's just a 32 wide SIMD unit that is doing it, doing the instruction across all of those. So whenever you make a variable, If this is different across all 32 threads, it goes in a VGPR, a vector general purpose register, and it has 32 of these, essentially. Whereas if this is the same across all of them, then it goes in an SGPR, and there's only one register of these, basically. See, under the hood, it's already doing the SIMD stuff automatically as part of the whole programming model. So this is why in shader code, when you have an if statement, which causes half of your threads to go into this one and half of your threads go into that one, the compute unit has to execute both sides of the branches, and it will run them at half capacity, right? Because half of them are going down this one, and then half of them are going down this one. So where you really benefit is when all of the all of the threads all of the SIMD lanes in a wave take the exact same branch. And then you don't get you don't go down the second branch. So because I'm using a K-mask register. What's a K-mask? So yeah, you could basically think of like, you know, ISPC. Is that what it's called? The Intel. Yeah, ISPC is, you know, this is basically this compiler is like what GPUs do, basically. Just never got around to using this thing. I just wish, you know, this stuff is more accessible on like CPUs. Like it's built into languages and stuff. But all these new languages don't really want to try and do anything cool. They just want to, you know, not do anything useful. Just make the syntax look nicer. Cool, so I'm happy about this. We can now simply just have a play around. So quickly, let's just figure out like, what are some like cool looking materials we could do? Like maybe we can make like, you know, I'll have a think. I'll look around the house. I'll see what sort of stuff we got around the house and stuff, and maybe. Did you just accept that you are dependent on GPU providers giving you their drivers? Have you looked into alternatives? Oh, you mean like free and open source drivers? Is that what you're referring to, Brian? Because the AMD one is open, and that's one I use. But I wonder if we can get like a... Is gravel not too great? Maybe that's not a good one to do. I wonder how you get all the different shades. Yeah, so effectively we want to try and like, with shaders, generate just... Generate our own textures with code. That's all we want to do. Have a bit of fun. And that don't look too great, does it? But I was thinking we can do like a volcanic ground or something. This might be fun because you can do like a missive on this one. And if we try and start with this one. Yeah, let's start with this one next stream. I think I can promise that one. Is there a closed part to the driver? Yeah, but we're not trying to make realistic stuff. Like, I think the idea is like, yeah, I'm not trying to create realistic textures, although, yeah, so it just all be, you know, people do it all the time. They do it in like other applications, but you can do it with shader code. And so we're pre-rendering them, and we'll save them out as images and pack them into a custom texture format or something like that, you know. But yeah, so is there a close part between the driver? I'm not really sure, but it's inside AMD. Yeah, I don't know. You have to have a look, to be honest. I don't really have the answers on it, but there is an open source driver and there's a closed source one as well. But yeah, I think we could do like a volcanic ground. It'd be quite easy, I think, to do something like this. We just have to figure out how to, like, there's already a sort of, there's a particular type of noise called the Voronoi edges, I think, and this looks close enough to that. It's just whether a case we can do it with a normal instead of an XY. I think we can maybe fudge something together. And then when you have, oh my days, why does that take you there? I don't like it when it does that. But yeah, I think we can use something like this to generate the gaps, and then we basically just try and shade. We can do whatever we want with the gaps, make them as thick as we want. And then we've even got like a distance on the inside, and we can use that to make some sort of ground, and it should be quite easy to do. Yeah, it's got to have a bit of a play. So I think this will be the first one that we do, and then when we have it done, we'll basically generate a bunch of ellipsoids in some kind of like box or something, and just see how they look next to each other. And if we sort of like generate different grids of them, maybe a bit of sort of like offsetted grids, and just see how they look like next to each other, and if it just looks good or not. And then we'll probably generate another wooden, a wood one, probably like a bark or something, or maybe like a wooden floor. You know, like planks of wood, basically. And we'll try something like that out. Yeah. AMD GPU, that's what I'm using. Okay, right. So the next stream will be on Thursday. About 2 hours, 45 minutes ago. I'm going to go ahead and get some sleep. And yeah, I hope everyone has a good Wednesday. Hopefully see you all on Thursday. If not Sunday, there's another stream. Let's go ahead and read this guy. So exciting stuff next stream. We're going to be working on some custom material stuff. But yeah, I'll see you all in the future one, guys. Catch you later. Bye-bye.